Welcome to the deep dive.
Yes, welcome everyone.
Here, we like to really get to the heart of complex topics.
Right to the core.
We take a whole bunch of information and,
Distill it down.
yeah, distill it down into something you can actually understand.
The essential element.
Without having to wade through a ton of technical jargon or,
Dense academic papers.
yeah, exactly. So today, we are going to take a deep dive into first-order logic inference,
That's right.
which sounds intimidating,
It can be.
but it's really about, how machines can reason logically.
Exactly. Like, how can we get a computer to actually think, to deduce things?
We're going to be drawing our information from a chapter that,
Lays out the different methods?
yeah, the different methods for answering questions.
Posed in first-order logic.
And the mission for you today, dear listener, is to understand how machines can do this.
To actually use logic to arrive at conclusions.
Kind of like getting a sneak peek into the engine of AI.
The fundamental mechanisms that make logical reasoning possible.
Okay, so let's jump right in. First-order logic, computers thinking. Where do we even begin?
Well, it's natural to want to start with something familiar.
Right, break it down.
So let's think about propositional logic.
Okay, so something a little simpler.
A bit more straightforward. And one approach is to see if we can translate our first-order logic statements into propositional logic.
Okay, use what we already know.
Exactly. Leverage those existing tools.
So how do we make that translation from first order to propositional?
Well, one key technique is called universal instantiation. We call it UI for short.
UI. Great.
So imagine you have a rule like, all greedy kings are evil.
Sounds like a good rule.
Formally, this would be x king, x evil, x.
Lots of symbols there.
It's the formal way to express it, but the
Okay.
idea is simple. If you're a king and you're greedy, you're evil. Now, UI lets us apply this rule to specific kings.
Oh, I see. So instead of this general statement about all kings, we can say something about a particular king.
Precisely. We substitute a specific king for the variable x. It's like saying, okay, let's look at King John. If he's greedy, then he's evil too.
So if we know King John is greedy, we can conclude he's evil because all greedy kings are evil.
Exactly. And we can do this for any king as long as we know they're greedy. Formally, UI says if we have a universal statement, EVI, we can infer SEBST, where V is a variable and G is a specific object, what we call a ground term.
Makes sense. We're taking a general rule and making it specific. But what about statements that aren't about everyone but just say something exists?
Ah, yes. That's where existential instantiation comes in. This is for statements that say there is something, but they don't tell us exactly what it is.
Like, there's a crown on John's head, but we don't know which crown.
Perfect example. We have the sentence X crown, X John. This says there's some X that's a crown and is on John's head.
But we don't know anything else about this X.
Right. Existential instantiation lets us give this X a temporary name. It's like saying, okay, we know a crown exists on John's head. Let's call it C1 for now. So we get crown C1 son head, C1 John.
C1 being this specific but still unknown crown.
Exactly. C1 is a new symbol, what we call a Skolem constant. It just represents that particular crown without giving us any extra information about it.
So we're not saying C1 is the only crown, just that it's a crown on John's head.
Exactly. It satisfies the existential statement.
Okay, that clears things up. So UI makes general rules specific. EI gives names to things we know exist. Are there any differences in how we use them?
Yes, a crucial one. UI can be applied multiple times to the same rule. For example, we could use the greedy king's rule for every king we know about.
So potentially a lot of specific instances.
Yes, whereas existential instantiation is usually applied only once. We introduce the Skolem constant, and then we usually don't need to use the original existential statement anymore.
Okay, so if I understand correctly, the strategy is to use these two techniques, UI and EI, to turn our first-order logic knowledge base into something that looks like propositional logic.
That's the core idea behind propositionalization.
We take all our general rules, make them specific, and then we have a bunch of simple statements that we can apply our usual propositional logic rules to. Sounds pretty neat.
In principle, yes. It can be a powerful technique.
But a catch.
There's always a catch.
What happens if we have function symbols in our knowledge base?
Function symbols. Remind me what those are again.
Like Father John. This takes an object John and gives us another object, his father.
Right, okay.
Now we can have Father John, grandfather, and so on.
Uh-oh, I see where this is going.
We'd have an infinite number of ground terms.
If we try to apply UI to all of them, we end up with an infinitely large propositional knowledge base.
Which, practically speaking, isn't very useful.
So our neat trick of converting to propositional logic hits a wall.
A rather large wall. What can we do about that?
Thankfully, there's a very helpful theorem that comes to our rescue. It's called Herbrand's theorem.
Herbrand's theorem. Okay.
This theorem tells us that if a sentence is entailed by our first-order logic knowledge base, then there's a proof of that entailment that only uses a finite subset of this potentially infinite propositionalized knowledge base.
So even though we could generate infinite ground terms, we don't actually need to consider all of them.
Exactly. If a proof exists, we can find it by looking at a limited number of these ground terms.
That's reassuring. So it's a complete method in the sense that if a sentence is logically implied, we can, in principle, find a proof.
Precisely. But there's another catch.
Another one.
What if a sentence is not entailed?
Can we always be sure about that?
Sadly, no. For first-order logic, there's no general procedure that can always tell us definitively if a sentence is not entailed.
So we might search forever and never know if we're just about to find a proof or if we're on a wild goose chase.
It's a bit like the halting problem. We can't always tell if a computer program will eventually stop or run forever.
Right, a fundamental limitation.
We say that the problem of determining entailment for first-order logic is semi-decidable.
Semi-decidable. This means we can create algorithms that will correctly tell us yes if a sentence is entailed.
But they might not always be able to give us a definitive no.
Exactly.
Okay, so propositionalization gives us a starting point, but it has some limitations. It brings us to our next topic, unification and first-order inference. It sounds like we're moving away from propositionalization and trying to work more directly with first-order logic.
Precisely. Propositionalization can be inefficient because it generates lots of specific instances that might not be relevant.
We'd rather have a more targeted approach.
Yes, one that uses inference rules that work directly with first-order logic sentences and only make the necessary substitutions.
Okay, so how do we do that?
One important rule is generalized modus ponens. Modus ponens, that's a familiar rule from propositional logic. How do we generalize it for first-order logic?
In propositional logic, modus ponens says, if we know P, and we know what P implies Q, then we can conclude Q.
Right, a basic building block of reasoning.
Generalized modus ponens extends this idea to first-order logic. It allows us to use substitutions to match the premises of a rule with our known facts.
So instead of it requiring an exact match, we can have a match up to substitution.
Exactly.
Okay, so let's go back to our greedy kings are evil example. We had the rule heir X, greedy, at the evil X. We also knew King John and greedy X. How would generalized modus ponens help us infer evil John?
Well, our rule has two premises, King X and greedy X, and the conclusion is evil X. We know King John, and from greedy we can get greedy John using universal instantiation.
So we have a match for both premises, but with John instead of X.
Right. If we use the substitution X John, then we can apply generalized modus ponens to conclude evil John.
So it's like we're plugging in John for X everywhere in the rule.
Precise.
Okay, that's pretty elegant. We're directly using the first order rule without having to generate a whole bunch of propositional instances.
And the key to making this work is a process called unification.
Unification. All right, tell me about that.
Unification is the process of finding a substitution that makes two logical expressions identical.
Identical?
Exactly the same.
Okay.
There's an algorithm called unify that takes two expressions and tries to find this substitution, this unifier, if one exists.
So if we have a question like, who does John know? We can represent that as knows John, where X is the person we're looking for.
Right.
And we can use unify to see if that matches anything in our knowledge base. Like if we have knows John Jane, unify would find the substitution in X Jane.
Exactly. Because if we replace X with Jane in knows John Jane, it becomes identical to knows John Jane.
Okay, I'm starting to get the hang of this. Can you give me some more examples of how unify works with different expressions?
Sure. Let's say we have knows John X and knows Z Bill.
Okay.
Unify would find the substitution X Bill John.
Because that makes both expressions knows John Bill.
Right. And if we have knows John X and knows Mothery, unify would give us Y John X Mother John.
Interesting. So we can even unify expressions with functions.
Yes, as long as we can find a consistent substitution.
What about knows John X and knows Olix Elizabeth? Can we unify those?
This one actually fails.
Why is that? It seems like if John knows Elizabeth and anyone known by John could know Elizabeth, there might be a connection.
That's a great observation. But the problem is that X can't be both John and Elizabeth at the same time.
Ah, I see. We can't have X meaning two different things within the same unification?
Exactly. To avoid these kinds of accidental clashes, we need to do something called standardizing apart the variables.
Standardizing apart, what does that mean?
It just means renaming the variables in one of the expressions so that they don't clash with the variables in the other expression.
Like if we renamed X to Z in nose, X Elizabeth, then we could unify it with nose John X without any problems.
Precisely. Unify knows John, knows Elizabeth, would give us Elizabeth's John.
Okay, that makes sense. So unify finds a substitution that makes two expressions identical. But can there be more than one such substitution?
Yes, there can be multiple unifiers.
Oh.
For example, for knows John, X and knows YZ, one unifier is Y John, XG, another is Y John, X bills is Bill Bill.
So one is more general than the other.
Exactly. We're usually interested in the most general unifier, or MG. It's the unifier that doesn't make any unnecessary assumptions.
So the MGU is like the most flexible way to unify two expressions.
You could say that.
And it's unique.
Unique up to renaming of variables.
Okay. So how does this unify algorithm actually work?
It's a systematic process that compares the two expressions piece by piece.
Looking for substitutions that make them match.
Right. And there's one important check it needs to do. It's called the occur check.
Occur check.
This prevents us from creating nonsensical substitutions, like trying to say that X is equal to father X.
Right, because something can't be its own father.
Unless we're talking about some very strange family trees.
Haha, exactly. But I can imagine this Archer check might slow things down.
It can add computational cost. Some older systems might skip it for efficiency, but that can lead to errors.
So it's a trade-off between speed and accuracy.
In modern systems, there are more efficient ways to handle the occur check.
Okay. So we have this unify algorithm. How does it fit into the bigger picture of how we store and retrieve information in a knowledge base?
Underneath the high-level operations of adding to the knowledge base, tell, and querying the knowledge base, ASK, are the more fundamental functions, store and fetch.
Oh, break it down for me.
Store is simple. It takes a sentence and adds it to our knowledge.
Straightforward enough.
Fetch is more interesting.
Mm.
It takes a query and finds all the sentences in the knowledge base that can be unified with that query.
So it uses unification to find matches.
Precisely. And it returns the unifiers, the substitutions that make the query match the sentences in the knowledge base.
So if we ask who does John know with knows, John, FTCH, would find all facts in the knowledge base that unify with that.
Exactly.
Now, if we just go through every sentence in the knowledge base and try to unify it, that could be very slow.
Especially if we have a large knowledge base.
Right. So how do we speed things up?
We use indexing.
Indexing, like an index in a book.
Sort of. It's about organizing the information in the knowledge base so we can find things more quickly.
Okay, how does that work?
A simple way is predicate indexing. We group all the facts with the same predicate symbol together.
So all the knows facts together, all the loves facts together, and so on.
Right, so if we're looking for knows John X, we only need to look in the knows bucket.
That's much faster than looking through everything.
But what if we have a predicate that's used in many clauses?
Like, employees X, used by a big company to track all its employees.
Yes. If we query employees X ledgered, predicate indexing alone wouldn't be enough.
We'd still have to look through all the employees facts. So what can we do in those cases?
We can index on multiple arguments.
So we could have an index for the second argument of employees, which would let us quickly find all the employees of Richard.
Right. And we could also have an index for the first argument to find all the people employed by a specific company.
So we can index in different ways depending on the kinds of queries we expect to ask.
Precisely. And there's this idea of a subsumption lattice that helps us think about indexing.
Subsumption lattice.
It's a way of organizing all the possible generalizations of a fact.
Give me an example.
So, employees, IDM Richard, is a specific fact, but it's also a specific instance of employees, X Richard.
Where X could be any company.
Right. And it's also an instance of employees IBM, where Y could be any person.
And the most general form is employees, X.
Exactly. These different levels of generality form a kind of hierarchy.
A lattice?
The most general form is at the top, and then we have more and more specific instances as we go down.
And the most general unifier helps us find the most specific common generalization of two expressions. Right.
Okay, so the ideal scenario is to index everything in every possible way.
Right. Well, ideally, yes.
But practically,
Practically, it's often not feasible, especially for predicates with many arguments or when we have functions involved.
because the number of possible generalizations explodes.
Exactly. So we need to be clever about how we index. We might use fixed indexing policies or adaptive policies that learn which indices are most useful.
Okay, so it's all about trade-offs.
As with most things in computer science.
So that covers unification and indexing, the groundwork for how we actually do inference. Let's now move on to forward chaining.
All right. Forward chaining is a data-driven approach to inference.
Data-driven. So
Yeah.
we start with the facts we know, and then we use the rules to derive new facts.
Exactly.
Like a chain reaction.
In a way, yes.
We keep going until we can't derive any more new facts.
Or until we've answered our query.
Okay. And this forward chaining typically works with a specific kind of logical expression.
First-order definite clauses.
Can you remind me what those are again? Sure. They're disjunctions of literals with exactly one positive literal.
Disjunctions, meaning or statements.
Right.
And a positive literal is one that's not negated.
Right.
And we can write them as implications.
Where the antecedent is a conjunction of positive literals and the consequent is a single positive literal.
Conjunction being and the consequent is what we're trying to prove. And any variables in these definite clauses are implicitly universally quantified.
That's right. We don't allow existential quantifiers here.
So our greedy kings are evil rule, king x equal x, is a definite clause.
Yes, it is.
And a simple fact like King John is also a definite clause.
It is because it's equivalent to King John false, which fits the form.
Okay, so it's a somewhat restricted form of first-order logic, but still quite expressive.
Indeed. Many real-world rules can be represented as definite clauses.
Can you give me a more concrete example of how forward chaining would work with these definite clauses?
Let's go back to our crime scenario. We can represent the rule, it's a crime for an American to sell weapons to hostile nations, as the definite clause, American X sweat Sherman X hostile criminal X.
So if someone is American, sells a weapon to a hostile nation, then they're a criminal.
Precisely. And suppose we have some initial facts. Let's say Nono has some missiles. Using existential instantiation, we can represent this as owns Nono M1 and missile M1, where M1 is a Skolem constant representing those specific missiles.
Okay.
We also might have the rule, missiles are weapons.
Yeah.
Missile X, weapon X.
Makes sense.
And another rule, an enemy of America is hostile. Enemy X, America. Hostile X.
All right.
And finally, some basic facts. American West and enemy known America.
Okay, so we have our rules and our initial facts. How does the forward chaining algorithm proceed?
It starts by looking at all the rules and seeing if their premises are satisfied by the currently known facts.
Using unification to match things up.
Right. If a rule's premises are satisfied, then we apply the unifier to the conclusion of the rule, and that becomes a new fact.
So in a crime example, the rule about Americans selling weapons wouldn't fire initially because we don't yet know if anyone sells weapons to a hostile nation?
Correct. But the rule missile sounds, Nachi's X no-no, can fire because we have missile M1 and owns no M1.
So we can conclude sells West M1 no.
Exactly. And the rule missile X weapon X also fires, giving us weapon M1.
And since no is an enemy of America, we can use the rule enemy X America hostile X to conclude hostile no.
Precisely.
So we've derived 3 new facts in the first round.
And now we repeat the process.
Check all the rules again, see if any more premises are satisfied.
Exactly. This time, the rule American sells XY's hostile X style C, criminal X can fire.
Because now we know that West is American, M1 is a weapon, West sells M1 to no, and no is hostile.
So we can conclude criminal West.
West is a criminal.
Our algorithm has successfully deduced that.
Now, this forward chaining, it seems like a very systematic way to derive all possible logical consequences.
It is. And it has some desirable properties. It's sound and complete for definite clause knowledge bases.
Sound and complete. Can you remind me what those terms mean in this context?
Soundness means that everything the algorithm derives is actually logically entailed by the knowledge base.
So we're not getting any false conclusions?
Right. And completeness means that if something is entailed, the algorithm will eventually derive it.
So it's guaranteed to find all the true conclusions.
At least for definite clauses.
Right. But you also mentioned that forward chaining can be inefficient.
Yes, there are some inherent inefficiencies in the basic algorithm.
What are the main sources of inefficiency?
Well, in each iteration, we have to check every rule against every combination of facts.
That sounds like a lot of checking.
It can be very computationally expensive, especially for large knowledge bases.
And we also end up checking the same rules over and over again, even if nothing much has changed.
Right. And the algorithm might generate lots of facts that are not relevant to the specific query we're interested in.
So lots of wasted computation.
Essentially, yes.
Okay, so let's look at these inefficiencies one by one. First, the matching of rules against facts. For a simple rule like missile X, weapon X, it seems straightforward.
But for rules with multiple premises, the order in which we try to match them can make a big difference.
So if we have missile X, we might want to try to find a match for owns known X first, because there might be fewer facts that match that compared to missile X.
Exactly. This is called the conjunct ordering problem. And it turns out that finding the optimal ordering is a hard problem.
Like NP hard.
Yes, NP hard.
But we can use heuristics to find a good ordering, right?
Right. Heuristics like the ones used in constraint satisfaction problems.
Mhm.
In fact, there's a close connection between pattern matching and CSPs.
Interesting. So even though matching in general can be hard, there are ways to make it more efficient.
And in many practical cases, the rules are simple enough that it's not a huge problem.
Okay, that's good to know. What about the second inefficiency, the repeated checking of the same rules?
The key insight here is that any new fact we derive must have been derived using a fact that was newly inferred in the previous iteration.
So we don't need to recheck all the rules, just the ones that might be affected by the new fact.
Precisely. This is called incremental forward chaining.
Incremental forward chaining, got it.
It avoids a lot of redundant computation.
Makes sense. And finally, the problem of generating irrelevant facts.
One way to address this is to use backward chaining, which is goal-directed.
We'll talk about backward chaining soon, but are there other ways to restrict the forward chaining process?
Yes, there are techniques like magic sets used in deductive databases.
Magic sets. Sounds intriguing.
The idea is to rewrite the rules based on the specific query we're interested in.
So we add extra conditions to the rules that filter out irrelevant facts.
Exactly. It's a way of focusing the forward chaining process on the relevant parts of the knowledge base.
Okay, so magic sets help us avoid going down rabbit holes.
You could say that.
That was a great explanation of forward chaining. Let's move on to backward chaining.
Okay. Backward chaining is a very different approach.
Goal-directed, you said.
We start with the goal we want to prove and work backward through the rules to see if we can find the supporting facts.
So if we want to prove criminal west, we look for rules that have criminal west as their conclusion.
Exactly. And then we try to prove the premises of those rules.
And so on, recursively.
It's like searching a tree, but instead of branching out from the root, we branch out from the goal.
An and/or tree, you called it.
Yes, because we might have multiple rules that can lead to the same goal, OR, and we need to prove all the premises of a rule to apply it, AND.
So it's a goal-directed recursive search process.
Precisely.
And you mentioned that backward chaining is often implemented using depth-first search.
Right. We explore one path in the search tree all the way to the end before we backtrack and try another path.
What are the advantages and disadvantages of depth-first search?
It's efficient in terms of memory usage, but it can get stuck in infinite loops if the search space has cycles.
And it might miss solutions that exist on other paths.
Yes, it's not guaranteed to find the shortest path to the goal.
Okay, so there are trade-offs. Now let's talk about logic programming in Prolog, which uses backward chaining extensively.
Right. Prolog is a programming language based on the idea of expressing programs as logical relationships.
And then we ask queries, and Prolog uses backward chaining to find the answers.
Exactly.
So a Prolog program is a set of clauses, which are essentially definite clauses.
And Prolog has a built-in inference engine that uses depth-first backward chaining.
It tries to match the goal with the head of a clause, and then it tries to prove the body of the clause.
Recursively.
You also mentioned that Prolog has some features that go beyond pure logical inference.
Yes, for practicality and efficiency, Prolog makes some compromises.
What kind of compromises?
Well, it assumes that different constants refer to different things, even if it's not explicitly stated.
That's the unique names assumption.
Right. And it assumes that anything that can't be proven is false.
The closed world assumption.
Exactly.
Those assumptions simplify things, but they might not always be true in the real world.
Right. And Prolog also has built-in predicates for things like arithmetic and input-output, which are not strictly part of logical inference.
And it might skip the occur check in Unification for performance reasons.
Which can lead to errors in some cases.
And it doesn't always check for infinite recursion.
So there are some situations where Prolog might get stuck in an infinite loop.
But for many practical applications, these compromises are acceptable.
And they make Prolog a very powerful and flexible language.
You mentioned an example where Prolog's depth-first search could lead to an infinite loop. It seems like the order of the clauses in a Prolog program can matter.
It can, yes. If we define our clauses in the wrong order, Prolog might get stuck.
So there's a procedural aspect to Prolog, which is different from the purely declarative nature of first-order logic.
That's an important point.
You also contrasted Prolog with forward chaining, saying that forward chaining is like dynamic programming.
In the sense that it builds up all the possible consequences from the facts and rules.
Is there a way to bring that idea of avoiding redundant computation into backward chaining systems like Prolog?
Yes, there is. It's called tabling or memoization.
Tabling.
The idea is to remember the results of subgoals that have already been evaluated.
So we don't have to recompute them every time.
Exactly.
That can save a lot of time, especially in recursive cases.
And it can also help prevent infinite recursion.
So tabling makes backward chaining more efficient and more robust.
Exactly.
And finally, you mentioned constraint logic programming, CLP, an extension of Prolog.
Right. CLP allows us to express constraints on variables rather than just binding them to specific values.
Can you give me an example?
Let's say we have a rule defining the triangle inequality. The sum of any two sides of a triangle must be greater than the third side. In Prolog, if we ask a query like triangle 3 for z, where z is an unbound variable, it might not give us a useful answer.
Because it doesn't know what z is.
But a CLP system could use its constraint solver to tell us that z must be greater than 1 and less than 7.
So it gives us a range of possible values.
Exactly. CLP is very powerful for dealing with problems that have large or infinite domains.
Like scheduling problems, optimization problems, things like that.
Right.
Okay, that's constraint logic programming. Now let's move on to our final inference method, resolution.
Resolution is a very powerful method.
And you said it's complete for all first-order logic knowledge bases.
Oh,